Welcome to our lectures on advanced power electronics and control. We shall continue with our device physics. Today we shall discuss a new entrant of this family is IGCT. So, full form of IGCT is that integrated gate commutated thyristors. I intentionally wish to choose these devices before very popular design device called IGBT, so that we can compare between both and we can find it out where it can find its applications. IGCT actually is basically a development on GTO. What are the drawbacks we have found in GTO? It is actually high dissipation in the gate. So, it is improved GTO. An integrated gate, that is the features of IGBT that essentially form BJT. When you got a insulated gate, that becomes IGBT. It is actually a combination of the advantage of the MOSFETs and the BJT. Here it is essentially a combination of MOSFET and GTO. So, integrated gate and also insulated gate and anti-parallel diode. MOSFET I will take at last. So, we shall understand it better. So, basically we are now moving essentially towards basically the power dimension and power rating available in the market. So, that is my selected chronology. So, first we have discussed about the SITh, which has a highest power rating capability, followed by GTO, thereafter IGCT. But there can be a debate which one has a more power handling capability, but cost, and since it is came little later. So, I have taken after GTO only because it is an improved GTO, we require to understand GTO. So, it is designed and manufactured so that it commutes all the cathode current away from the cathode region and diverts it out of the gate contact. So, this is one of the biggest advantage of it. IGCT will just come little later, similar to the GTO in a structure, except that it has low loss N buffer. That is actually the one advantage of it. We had a N buffer region, here also you have a buffer region, but it is low loss between the N base and the M emitter. So, conduction loss of the IGCT is considerably low than the GTO. IGCT device package is designed as a result of the very low parasitic inductance. That is one of the actually requirement of the high DIDT. So, if there is a parasitic inductance, it will prevent DIDT and integrated with the special design gate drive circuit, but it is little complex. The gate drive contains all the necessary DIDT and DVDT protections. This package comes with that, basically this is manufactured by the ABB. So, it has come as a package. So, no other company, most of my belief and knowledge are now manufacturing it, still it is a sole patent of ABB. The only connection required is a low voltage power supply for the gate drive and an optical signal for controlling the gate. So, it is quite compact. So, you require optical isolation, you can sit somewhere and this will operate from a distant location, and this is quite requirement for the high voltage application for the safety and all. The specially designed gate drive and the ring gate package circuit allows IGCT to be operated without the snubber. So, we will talk about the protections and the gate driver of the design after actually discussing all the devices. So, for the DVDT and DIDT protection, mostly for the DVDT protections, we require snubber, but this has add-on features that it does not require snubber. and to switch the higher DIDT than the rating of the GTO. Only thing is that it is an improved version, thus it has all the improvement. Only one disadvantage is still it is mostly it is single sourced, and another issue was it still lies that actually it is quite costly than the rating of the same rating GTOs. So, this is the device structures cathode and anode, and this is actually N buffer region. It is doped in such a way it does not offer a very high on-state resistance, and in between there is actually silicon doping level is prescribed by the color. This is the highest doping level and this is the lowest doping level where it is this. And this is the actually symbol of this device. You have a gate, cathode, anode, and this is the practical device. It comes with the heatsink and everything. It is a quite compact. It is a something like plug and play device. Nowadays this term is used, plug and play. So something like that. You just connect the gate driver circuit and it will operate nicely. But problem lies if there is any fault inside it, you have to throw it out. So IGCTs are available with or without reverse blocking capability. So that is the manufacturer. You can choose a different kind of IGCT as you require. If you require for the actually application like VSI and you are feeding an inductive load like your for drives and all those things, where you require to have a forward blocking mode but bidirectional current mode, then generally it comes with anti-parallel diode. Reverse blocking capability adds to the forward voltage drop because it need to have a long and the low drop P region. IGCT capable of blocking reverse voltage is known as the symmetrical IGCT, as abbreviated same as your GTO. So, it is SIGCT. IGCT incapable of the blocking reverse voltage by putting the anti-parallel diode, then it becomes a asymmetrical IGCT or abbreviated at AIGCT, that is quite frequently used in VSI kind of applications. While let us understand it, actually in case of the voltage source inverter, so you generally require current to be bidirectional, and for this reasons in case of the if it is IGBT, you have to provide the anti-parallel diode. Because if you have a lagging power factor, then what happens, then one voltage is positive, then current also be negative. Then also this actually the anti-parallel diode comes into the picture. Ultimately, so in this kind of application you have to provide this kind of anti-parallel diode, and that makes it the configuration asymmetric. Asymmetrical IGCT can be fabricated with the reverse conducting diode, that is what I was saying, in the same package, and it is known as RC IGCT, and you can have a very fast recovery diode. That is an advantage because it does not have a body diode unlike MOSFETs, and so you can choose a very high conducting and high featured anti-parallel diode depending on the kind of switching frequency you are using. Now, this is the structures of the MOS-controlled thyristors, or this is another member of the thyristors, that is called MOS control. The only difference is that you have this gate driver part has been modified by using the two MOSFETs, and MOS-controlled thyristors is a voltage controlled, fully controlled thyristors. It can turn it on and turn it off by this MOS devices, but power rating and power handling capability of is very low compared to the IGCT, because it is basically it comes from the gate driver part is totally MOSFET, so power handling capability is quite low. MCTs are a similar in operation as GTO, but have a voltage control insulated gate. They have two MOSFETs opposite conducting types in their equivalent circuit. One is responsible for turn on, mostly the upper one, and other is responsible for the turning off. So, positive voltage on the gate terminal with respect to the cathode turns the thyristor on the on state, and the negative voltage on the gate terminal with respect to the anode which is close to the cathode voltage during the on state, turns this thyristor off. So, you will operate at a gate voltage. Since it is an insulated gate, very low amount of current will flow. Thus, power dissipation in GTO was a big concern, and that aspect has been considerably reduced, but problem lies, actually its power handling capability is quite low. So, another members of the thyristor is called static induction thyristors. So, there actually it is field controlled thyristors or FCT or field controlled diode, and it has a features like the minority carrier device, a JFE structures with an additional injecting layer is been provided by the method of induction. Power handling capability is similar to the GTO, faster switching speed than GTO. This can be actually, these are the few add-on now comes into the pictures in GTOs. Normally on device, and problem is it is normally on. So, you have to have a normally off by applying the gate voltages by method of induction. Not convenient and could be normally off, but even for the higher on state losses. So, this is the one problem. We want the switches to be normally off. When a switch become normally on, there is a disadvantage. So, for this reason, if you can make it the switch actually normally off, but problem lies then the conduction losses will be considerably higher, or the advantage of it will be missed out. This device essentially a pin diode with a gate structure that can pinch off the anode current. Higher power SITs have subsurface gate or buried gate structures and allow larger cathode areas to be utilized. Hence, larger current densities are possible, but still actually it is not pretty commercially viable and is not quite available also in normal ratings and the design required. So, hopefully these are the development, but among this development of course, this IGCT is the forerunner, and hopefully this device will catch up in different kind of power electronics applications. Okay. Now, let us come across power metal oxide semiconductor field effect transistors. So, that is FET. We have studied FET in the linear electronics or the low power electronics. It is same thing, but you will find that actually power rating is at least 100 or 1000 times higher. FET can be operated at a very high switching frequency and has a very low losses, gate losses. So, these are the two actually the features, and for this reason actually we have a MOSFET, and from there we have this P channel and the N channel MOSFET. These are the very frequently used in low power electronics devices, mostly in DC to DC converter for its compact size and high frequency applications. So, this is the structures of the MOSFET. We have actually VDS, that is drain to source voltage, and we call drain and the source. Generally high voltage side is said to be the drain and other side is said to be the source. And we have GS, that is connected between this actually source and the gate. And what happened, actually this is called drain and this is called source. Then it can be actually different kind of MOSFET, that is enhancement MOSFET, depletion MOSFETs. Whenever you have giving a pulses, so there will be an induction, and generally it has a silicon dioxide or any kind of insulating medium, there will be a capacitive effect, and due to that induction there will be a charge carrier, then the channel will be formed, and with this channel current will flow. So, essentially, so it is insulated, current flowing through it will be quite low, but since there is a capacitor, so I equal to C dV/dt. So, ultimately whatever will be the gate pulses frequency into C, that will be the amount of the I, but since value of the C is quite low, thus current also will be quite low. So, you allow to go to the higher frequencies. So, this is the one of the layer So, this is actually the PN junction reverse biased, and offset voltage appears across the N region. So, channel required to be formed because this is the channel is broken. Once we apply a voltage, there will be a channel formed. So, that will actually carry the current, and this is called normally off kind of MOSFET, and this is we generally prefer. An N channel MOSFET, since the conduction devices are electron, so channels is made of electron, this is quite faster than the P channel devices. So, most of the application we prefer N channel MOSFET over the P channel MOSFETs, but in few application avoiding short circuit conditions, the combination of N and P MOSFETs are used, so that once upper thyristors is on, lower thyristors is automatically on, having a negative gate voltage and vice versa. So, in that case we use P channel, but you have to sacrifice on the switching frequencies. So, these are the few takeaways from here. The PN junctions is slightly reverse biased. Conducting channel is used to be conducting channel is induced by the positive gate voltage in case of the N channel MOSFET. Drain current flows through the N region of the conducting channel. Total resistance includes the resistance of the N region and the conducting channel and the source channel. But doping is so high that the resistance of these devices is quite low in the range of the milli ohm region. So, this is the typical characteristics of the MOSFET which you have studied into the analog electronics. So, this is actually drain to source voltage, and these are the different actually gate voltage. So, ultimately this region is basically the saturation region. So, and this region is a active region we want, and this region is a cutoff region where actually gate voltage is quite low, and we want basically to operate our devices in the active region. So, this is the switching characteristics of this MOSFET. So, you turn it on, thereafter since there is a capacitor effect, there will be a RG, there will be actually RS, and so it will actually charge these things. So, voltage will build up across this gate, and gradually what will happen, then current also will try to flow from this. So, there will be a TD, that is a delay time, where actually this UP is a pulse, and this is basically the voltage across this driver. So, it will take some time to grow. Once it reaches 10% of it, then you will see that actually current start picking up. Once actually gate current reaches the 90% of it, then you will find that it almost reaches the total current, and gate current will saturate here. Thereafter, at this point you decided to turn it off. So, for this reason what will happen, it will gradually fall, and you have to give little bit of negative voltage to turn it off and take out the charges in the tap region to make it off. So, you require to have a little bipolar of the supply. So, this is one of the MOSFETs data sheets which is frequently been used. This is the data sheet of the P channel MOSFETs. So, what is important here, mostly few aspects. This is basically the gate characteristics. This is a gate to source charge. So, depending on this actually your driver, if your power sinking capability of this driver, let us say some ampere, 0.5 ampere or 1 ampere, then this has to be filled. So, that kind of switching frequency you can go. Similarly, you will have a drain to source, and if you divide it by voltage you get the capacitance. Few data sheet also specify the capacitance. You see that a turn on delay which you have find it here, turn on delay. So, this delay is essentially will be actually in the range of 15 to 30 nanoseconds. So, it can easily be operated in the range of the megahertz level. Similarly, rise time it is this. Thereafter, you got this is the typical values. So, you will take this column only, and thereafter turn off delay is around 56 nanosecond, and this will be 36 nanoseconds, and recovery time is around 40 nanoseconds. So, these time what we have talking in the case of the microseconds, now it is nanoseconds. So, thus it can be used for the high switching frequency kind of application. However, what is the difference between that? The current handling capability of these devices are quite low, it is just minus 4.6 ampere, and also there are few aspects that gate threshold voltage required to be of this region, and apart from that you require basically to be operated in the range of the 70 volt, quite less than the other voltage. So, VDS can be 500 volt, but where we are talking about 1000 volts and more than that. So, drain to source voltage will be this, and VGS voltage source will be plus minus 30, and ID for 25 degree centigrade it can be around 10.6 ampere. So, for the 100 degree centigrade, well, it has to be derated, so it has to be this much, and then current if it is pulse kind of waveform, so it can be as high as 42 amperes, and these are the data sheets you have to design. We will show it how to design, and this is the values of the different capacitance. So, this is for 1 kilohertz and VGS equal to 0 and VDS equal to 25. These are the value will come out. Input capacitance will come into the picture. This is basically the CGS will generally represents the input capacitance. So, that will be around 1480. Output capacitance is this much. Generally it is close to the same values of the DS, but we have to draw the actual circuits, and the reverse transfer capacitance is about this much. So, these are the actually the data sheets of a MOSFETs, and from there you require to design one circuit where it finds its application. Mostly since for this high voltage frequency application and low power rating, low voltage setting also, it finds its application mostly in DC to DC converter. Now, you can see these are the turn on time are in the are in nanoseconds. So, QR, so this is the values, these values also in microsecond, and for this reason these devices can be operated in a very fast mode. Now, let us come to the another important member of this power electronics, that is insulated gate bipolar transistors. This invention itself is a mark of the change of the phase of the power electronics. So, Dr. Baliga in General Electric discovered it, and we are Indian, so we should be proud of his discovery. IGBT is preferred over the MOSFET because of its on state loss as compared to the MOSFET with a very easy driving process. But actually we have seen a very short lived another device which we have not discussed, it has been actually discarded, that is BJT, power BJT. Because of the high current it has been put off. So, Professor Baliga actually integrated the power BJT and the MOSFET and came out a new device called insulated gate bipolar transistors. So, it can handle the power of kilowatt to the, even it is possible to have a megawatt level. Generally we ranges varies and we are very frequently used for our day to day application in a kilowatt level, and it is a range in this kind of application that is mostly for the medium voltage drives applications, and all the invention and the development of the topology were based on these devices. So, multi-level inverter and all those things for high voltage applications was considering this IGBT. So, it is very important member of it. What happened here actually it is this part is essentially the MOSFET, the gate part is MOSFET, and this part is basically the transistors, and for this the symbol is this. So, in between you definitely get a transistors, that is PNP, and in between you also will get a MOSFET. So, this part is a transistor and this part essentially is the MOSFET. It has a multi-cell structures. So, it is combinations of the MOSFETs and the BJT. The basic structure is same as power MOSFET, only one extra region is there. During on state, minority carrier are injected into the drift region, which leads to the conductivity modulation. That means conductivity increases. It has slower switching time, less on state resistance compared to the power MOSFET, and so it can have a higher power handling capability. So, it can be used for the high voltage applications up to 700 or 2000 volt, and this is basically the MOSFET part of it, and this is basically the transistor part of it, and this is the drift region. So, this is the MOSFET part of it, and PNP constitute this basically the transistors, and so this is the model, and body spreading resistance is there. So, this is the body spreading resistance. What happened, that will handle, gives you a forward blocking capability. So, for this it can be used for the high voltage applications, and this is the drift region resistance. This is basically the drift region resistance. So, by changing the value of the resistance you can operate faster or slower. But what happened then, if you have a lower drift region resistance, you will find that power handling capability of the device is considerably reduced. These characteristics same as the characteristics of the BJT, which you have studied in the normal BJT applications in your analog electronics. So, this is your load line, and this is the IC and VC, and this is for the different kind of, instead of IB you will have the gate voltages. This is the only change. So, you will have this transconductance. So, for this reason this is the actually power line, and accordingly you will have a VG, it is for the current IC for the different values of VG, and this region is a saturation region. Then generally we do not operate these devices in the saturation region, then gate resistance control we try to actually maintain into the active region, and this is the cutoff region as same as from the BJT. So, we require to find it out actually the linear region of it. So, that is this part is almost linear. So, for this reason this is the transconductance we try to incorporate, and this will be the values of the IC versus GE. Now, this characteristics is same, you give a pulse. Once you give a pulse, when it is actually this is till you will find that when actually this applied pulses has come to the 10% of the value gate pulses, then everything will start. Once it almost reaches 90% of the value, then you will find that actually current through these devices will go to the only 10% of this device, and same way also you will find that voltage will start topping from this point. Once it reaches the 90% of the value, you will have a double slope characteristics. This is called punch up devices. So, it will fall this much. Thereafter, in remaining time it reaches the maximum value of the current. So, and it will have a different slope. So, it is a double slope characteristics. So, this IGBT has a unique features. All the device had a single slope turn on process, but IGBT has a double slope turn on process. So, but there is a difference between both the devices. In case of the IGBT turn off occurs due to the stored drift region. So, for this reason what happened, in this region, it will droop subtly. Thereafter, once it reaches only 10% of it, then voltage will drop and will settle down to the on state voltage, and from there we try to measure that whether it is going into the active region. We do not allow this IGBT to go to the saturation region, then short circuit condition will prevail. So, these are the few important aspects of the IGBT. Maximum collected to the emitter voltage is said to be the VCS. Maximum continuous collector current is IC, that we will see in the data sheet. Maximum pulse collector current is ICM. Maximum gate emitter voltage is VGS. Collector leakage current in on state is actually ICS. Gate emitter leakage current IGES. Collector emitter saturation voltage is VCE-SAT. Gate emitter threshold voltage, these are the important parameters of VGTH, that is the Thevenin equivalent of it. Forward transconductance GS, which we have shown in the graph. Input output transfer capacitance, as we have seen in the MOSFET data sheet, is ICS, OS and IRS. Switching time, that is rise time, for fall time, reverse time, and for the different mode. Maximum total power dissipation, PT max. So, what are the difference of the MOSFETs and the IGBT? MOSFET is applicable for the high frequency applications. So, improve switching speed, but in case of the IGBT we have a improved production technique that leads to optimal switching frequency, not as high as that MOSFETs, but it has got a higher current and a voltage handling capability. Improved dynamic performance that requires even less power from the driver. So, we have optimized basically the efficiency energy point of view this MOSFETs. Improved due to the overload for higher loading and all. Lower gate to drain feedback capacitance. Improve parallel current sharing capability. So, if you use the current handling capability of this driver to be increased, so you can put into the operation this parallel devices. Lower thermal impedance in turn has enabled much better power dissipation. Faster and smooth turn on and turn off waveform, we have seen there is a punch through. So, with while turn on there is a voltage drops in a two curves, that leads to better mode of control of the short circuit protection. Lower rise and fall time, which has allowed for the operation of the high switching frequency. So, lower on state switching losses, thermal impedance is quite low and lower input capacitance, so that you can put this faster operation. If it is a higher capacitance, so ultimately you require more current or the less frequency. So, this is the one of the data sheets of the IGBT. So, this is the rating, this is a quite low rating IGBT, because we have tried to choose the same rating of the MOSFETs. So, close to that rating we have chosen an IGBT. So, for this it is 600 volt, but you can see that current rating there was only around 10 ampere, it can go actually as high as 90 ampere. So, the huge actually improvement on the current rating part of it, and these are the few parameters, that is T on, it was quite high, it was around 10 or 15 in case of this, it is a double, but anyway, so but current is also double. So, you have to, this is TR is around 81, TD is 142, TF is actually around 74. So, these are the all the datas. Thank you for your attention. We have complete our discussions on the device physics part, and in next class we shall analyze the devices, and we shall discuss about the gate drive and little protections part of it, and thereafter we shall start with the normal topology. Thank you for your attention.